Hello students, welcome to our first classes, and this is Isi M.Math 2020 solution. I am solving question number 5. In the past two videos I have solved 1, 2 and 3, 4. So in this question, J be a 2 cross 2 real matrix as that J square equal to minus I, and I is the identity matrix. We need to show that if V belongs to R square and V not equal to 0, then the vectors V, J, V are also belongs to R square are linearly independent. So assume that there exist scalars alpha and beta such that alpha v plus beta jv equal to 0. So apply j to this equality, we get alpha jv minus beta v equal to 0. From these two identities we get alpha v beta jv minus beta alpha jv minus beta v equal to alpha square plus beta square into v equal to 0. Okay, so the first part is proved. Now coming to the second part, so that there exists an invertible 2 cross 2 real matrix in U such that uj u inverse equal to 0 minus 1 1 0. So let V be a matrix in the first column given by the vector V, and the second column is given by the vector first column, and the second column is given by the vector JV. So V equal to V JV. Now V is invertible. Now since V and JV forms a basis in R square, so let U equal to V inverse. Then JV equal to what? JV J square V. So JV and minus V. So V JV 0 minus 1 1 0. So if I just multiply, so take this V, so 0 minus 1 0 1 and 0. Okay. So in this case, U inverse equal to V inverse JV. So 0 minus 1 1 0. So since V not equal to 0, so we get alpha square plus beta square equal to 0 and alpha equal to beta equal to 0. So linear dependence of V and JV are proved. Next one. It's question number 6. Suppose that V is a three-dimensional real vector space. Okay, is a linear map such t square equal to 0. So that there exists a vector such that this set is a basis of V. So let V belongs to capital V is such that t square V is not equal to 0. So we assume that V, TV and t square V, all these three are linearly dependent. Then there are scalars like ABC such that AV plus BTV plus C t square V, it's the easier one. This, so apply T to this identity, we use TQ equal to 0 is the fact. So A TV plus B t square V equal to 0. So apply T to this identity using T cube equal to 0, we can get to this value t square V equal to 0. So A into t square V equal to 0. Now suppose AS V is another linear map such that SQ equal to 0 and S square equal to this, so that there exists an invertible linear map U V to V such that S equal to UT U inverse. Okay, so now let in the second part V belongs to V be such that again the same type of format TV and T square V. Now this time forms a basis. So V TV t square V forms a basis. So once it forms a basis, So let W equal to this whole thing. So this is be a matrix. Let it be a matrix. Let W be a matrix whose columns are given by the given vectors of V, TV and WV. So obviously W is invertible. So we have TW equal to T square V and 0. With respect to that we can represent the matrix. So V, TV and T square V. This will be multiplied by 0, 0, 0, 1, 0, 0, 0, 1, 0. So this is nothing but W into the same thing. So this follows that W inverse TW equal to also this thing. Okay, so for some invertible matrix W. So let if S be another linear map of V such that A square not equal to 0 and S cube equal to 0, then say for the some invertible matrix Q we can have this Q inverse S into Q equal to, okay. So now Q inverse SQ is nothing but W inverse TW and S equal to U inverse. So for this U equal to QW inverse, but T square V not equal to 0. So A equal to 0 and consequently B equal to 0 and that consequently C equal to 0. So this is, there is a linear independence in these and that is proved.